take a look at number 2 in section 10.4. We're going to consider this series, and we're going to determine whether the series converges absolutely, conditionally, or not at all. So obviously, when we look at this, you might take a look at the terms that we're adding up. Notice as n goes to infinity that these terms are indeed going to zero, because the sign of whatever quantity is always going to be less than uh, 1 in absolute value. So it will range anywhere from -1 to 1. But clearly, as n goes to infinity, n squared is just going to infinity. So any constant between -1 and 1 divided by something going to infinity is going to go to 0. We can consider now whether or not this series converges absolutely, though, by taking the absolute value. All right. And as we've already said, the absolute value of sine of pi n over 5 is less than or equal to 1 in absolute value. So when we look at this expression, it's going to be equal to this because, of course, n squared will always be positive or n greater than 0, and we're starting at n equal 1. And so this fraction is always less than or equal to 1 over n squared. So let's think about this corresponding series. That is a convergent p series, right? Remember, p series converge for p greater than 1. And so this is a convergent p series. But our terms of our series that we're looking at are always less than or equal to terms of this series. And therefore, our series, the absolute value that is series here, converges by direct comparison. But that means the original series converges absolutely and hence converges. And so we do conclude that the original series converges absolutely. Notice I could not conclude this simply by noting what I started with, that the terms of the sequence that we're adding up go to 0. Remember, that tells me nothing, just that it has a chance to converge. And so the real proof is in showing that by direct comparison, the series is absolutely convergent. Okay, hope this helps.